Welcome to UGC lecture series Linear Integrated Circuits. In this class we are going to discuss about the analog multiplier, applications of analog multiplier, and one of the application of operational amplifier in open loop configuration, that is the comparator. So first is analog multiplier. Analog multiplier is a device which takes two analog signals and produces an output with which is their product. Such circuits can be used to implement related functions such as squares, square roots, division and frequency doubling, and so on. An electronic analog multiplier can be called by several names depending on the function it is used to serve. So these are the applications of analog multiplier: the frequency doubling, measurement of real power, detecting phase angle difference between two signals of equal frequency, multiplying two signals, dividing one signal by another, taking square root of a signal and squaring a signal. So these are the applications of analog multiplier. This is the symbol of analog multiplier, where Vx and Vy are the two input signals and Vout is the output signal, and this is the output is expressed as the product of the input signal divided by a scaling factor k, Vx into Vy divided by k, where k is the scaling factor. And this analog multiplier can be of these types: single quadrant analog multiplier, two quadrant and four quadrant. In single quadrant analog multiplier, the input signals Vx and Vy will be in unipolar. Vx is unipolar and Vy is unipolar, so the output is unipolar, drawn like this. Take the x-axis Vy and Vx, y-axis for Vy. So here these two input signals are unipolar in the sense Vx is positive, Vy is also positive. So the output will be in positive direction. So all are unipolar. And two quadrant analog multiplier shows that Vx is bipolar, Vy is unipolar, so the output is bipolar. For that I can draw Vx in both the direction, positive as well as negative, and Vy only one direction, not here, not in the negative direction of Vy. So Vy is only one direction, so it is unipolar. Vx in both the directions, so it is bipolar. So the output will be in bipolar, either it is a positive or a negative output you will be getting. If any one of the input signal is negative, then the output may be a negative output signal according to the combination of Vy and Vx. And four quadrant multiplier, in this case all are bipolar, Vx, Vy and the output. Or in all the direction you can get the output. Vx is in both the direction, that is positive direction as well as in the negative. Vy is also varies from positive to negative. So the output will be in either polarity, either it is a positive value or it is a negative value. So these are the types of the analog multiplier. According to the input varies from one direction, one region to the other region, or a quadrant you can say. The multiplication using logarithmic amplifier. The logarithmic amplifier is also used for multiplying two signals. So this circuit, the first circuit, shows you the multiplication using a log value, where x is input for one logarithmic amplifier and y is another input for another logarithmic amplifier. So if you add these two values, then you will be getting natural logarithm of, you know that the logarithmic value will give you a natural logarithm of the input signal. So the output at this point, the summing point, you have the value of Vx into Vy. So after you take the antilog value of this particular input, then you will be having the product of the input signals x and y. So, this is the multiplication of the multiplication using log and anti-log amplifiers, and this circuit is a division circuit where you, instead of a summing point, here you have a subtraction point. Here natural logarithm of Vx by Vy. So, you have a circuit, you have an output after the anti-log amplifier as x by y. So, now the log anti-log amplifiers are used for multiplication and division. So, this restricts the amplifiers to one quadrant operation. Why? Because the signals must be in the same polarity for log anti-log amplification. The input as well as the reference voltage must be in the same polarity for log. If you use a log anti-log amplifier for multiplication as well as division, so this restricts to a single quadrant operation here. So, next is we will see the application of an analog multiplier. So, this is one of the application, frequency doubling. The multiplication of two sine waves of same frequency but of different amplitudes and phase allows to double a frequency and to directly measure the real power. If you consider, so you have to give two sine waves of same frequency but with different amplitudes and phase. So, I am using two frequencies. Say Vx is the amplitude of the Vx is small Vx sine omega t, and Vy is the next sine input. Its amplitude is small Vy sine, its frequency is same but with different phase. So, omega t plus theta. So, these are the two input signals I am giving for a analog multiplier. So, in this circuit, this is the analog multiplier symbol. So, here Vx is takes the value of Vx sin omega t, and Vy takes the value of small Vy sin omega t plus theta. So, now we are going to see how the frequency is doubled by using the analog multiplier with this two signals with same frequency, different amplitude and different phase. So, normally the output of the amplifier will be Vx Vy by V reference. This V reference is set to 10 volts, and this is actually lesser than the saturated value only when this Vx and Vy must be less than this V reference. So, this is the normal output of the analog multiplier circuit. So, if you substitute instead of take this as capital X capital Y here. So, substitute the values what we have given. So, Vx sin omega t into Vy sin omega t plus theta by V reference. So, now Vx Vy by V reference, if you take out, these are the amplitudes. Now, the remaining terms are sin omega t plus theta. So, if you substitute the trigonometric equation for sin omega t plus theta, this is in term of, in the form of sin a plus b. So, for sin a plus b, it is sin a cos b plus cos a sin b. Now, you multiply the sin omega t with the terms. So, you will get sin square omega t cos theta plus sin omega t cos omega t sin theta, if you multiply the sin omega t inside these two terms. And now, what is for V naught will be Vx Vy by V reference. If you multiply the term, you will be getting sin squared omega t cos theta plus sin omega t cos omega t sin theta, sin omega t cos omega t, and here sin theta. This sin squared omega t or sin squared theta can be written as, this is a trigonometric formula. It is 1 by 2 minus cos 2 theta by 2, and also this sin omega t cos omega t, this is written as sin 2 omega t by 2. So, if these two values are substituted in the above equation V naught, you will have Vx Vy by V reference into cos theta 1 by 2 minus 1 by 2 cos 2 omega t plus these two terms is replaced by this sin 2 omega t by 2 sin theta. Now take 2 outside, Vx Vy by 2 V reference, and now multiply this cos theta inside, cos theta minus cos 2 omega t, these two will be got out. So, you will get only cos theta minus cos 2 theta, cos 2 omega t cos theta, plus here sin theta sin 2 omega t. If you multiply this Vx Vy 2 by 2 into V reference, Vx Vy by 2 into V reference inside, you will have this term cos theta into this, and the remaining terms as Vx Vy by 2 V reference. If you take minus out, if you take plus out, then it is sin 2 omega t sin theta minus cos 2 omega t cos theta. So, these are the two terms you will be getting for the output voltage. Here this first term is a DC term with only phase value cos theta. There is no frequency in the first term, and in the second term, if you multiply the term Vx Vy by 2 V reference inside, you will get a DC term with only phase cos theta, and if you take plus outside instead of minus, you will have sin term first, sin theta sin 2 omega t minus cos theta cos 2 omega t. So, this is the second term, you got it. So, this is the DC term, and this is twice the frequency of input. So, here we have given sin omega t, but now we have obtained sin 2 omega t. This is actually the frequency term, twice of the frequency of the input signal. So, in such a way that the analog multiplier is used for frequency doubling for the input signals Vx and Vy. This is one of the application of the analog multiplier, and next is the voltage divider. So, in this case the multiplier circuit, in this case the multiplier is present in the feedback path of the operational amplifier. When you look at the circuit diagram, the input voltages are given here. One input voltage, say this is Vx, this is Vx, Consider this as Vx and this is V out and this as Vz. It is not actually clear. So I have taken this voltage as Vx and this voltage as V out, this voltage as Vz, and consider this voltage as Va. Since the printed terms are not clear, so I have replaced everything as new. And when you look at the circuit in the operational amplifier's feedback loop, there is an analog multiplier circuit. So this is the setup for the voltage divider. The output of the analog multiplier is given as the input for the operational amplifier to the non-inverting terminal of it, and positive terminal is grounded through the resistance or compensation, and Vz is given through input resistance R to the negative terminal. And now if you obtain an equation for Va, that is the output of the analog multiplier, normally it is the multiplication of the two input signals divided by the V reference voltage. So Vx is one of the input signal, V out is another input signal divided by V reference. This is the voltage for Va, and from the circuit Va can also be written as I2 into R, and now I2 is written as Vx V out by V reference into R. This is I2, and at A, if you apply KCL, I1 plus I2 is equal to 0. So I1 is equal to minus I2. So here I1 is written as minus Vx V out by V reference into R. So from the circuit, Vz is given as, Vz is given as I1 into R. Substitute I1 in this equation. So minus Vx V out by V reference into R. So these two R will be cancelled, and Vz is equal to minus Vx V out by V reference. So V out can be written as V reference into Vz by Vx. So Vz is divided by Vx, and these two voltages are given externally. Vz divides the voltage Vx and it is multiplied with the constant voltage V reference here. So in this way, this voltage divider, this analog multiplier is used as a voltage divider. So whatever the voltage is given at this input terminal of the analog multiplier, which divides the voltage given to the operational amplifier in its inverting input terminal. So from the circuit, you can see that the output voltage is Vz by Vx, both are given externally to the entire circuit. And this is another example or another application of multiplier. So here this is a voltage squarer circuit. So can you just tell me what is the output of this squarer simply? So output voltage is given as V square by V reference, that is Vi square by V reference, because if the input voltages are shorted and given with only one input signal, say Vi, and this is going to be the square at the output. Why? Because the output of the analog multiplier is Vx into Vy divided by V reference. If Vx and Vy are one and the same as Vi, then it is Vi square by V reference. So, these are I have just given 3 applications. One is the frequency doubling circuit, frequency doubling. For this, the circuit is actually just the multiplier circuit. Multiplier circuit, you have to give Vx, you have to give Vy and take the output Vout. Vx is Vx sin omega t and Vy is Vy sin omega t plus theta. So, this is the circuit of the frequency doubling, for which we have derived the output of the circuit, and which shows that one of the term is the DC term, the other term is the term which has twice the frequency of the input signal. So, the frequency is doubled here. Next is voltage divider we have seen, and voltage squarer also we have seen. And next is one of the important application of operational amplifier in its open loop configuration. If there is no loop present, if there is no loop in the from the output to the input, and only the input signal is given to the positive terminal and as well as to the negative terminal, then the output will be a saturated value according to whatever the according to the magnitude or amplitude of the input at its terminal, input terminal. The output will be either a positive V saturation or a negative V saturation according to the input. And there are 2 types of comparators, one is inverting, the other one is non-inverting comparator. For an inverting comparator, the signal must be given to the inverting terminal. Here it is actually we have to change. So, this is a non-inverting comparator. Signal is given to the non-inverting terminal of the operational amplifier, and if you look at the loop, there is no loop present. Normally for an amplifier or a voltage follower circuit or an integrated differentiator circuit, for any circuit whatever we have discussed earlier, there is an feedback path from the output to the input through a resistor or through a capacitor. So, here there is no feedback from the output to the input, just we have given the input signal and the reference voltage. Input signal is given to the positive terminal and the reference voltage is given to the negative terminal. If the input is given to the positive terminal, then it is said to be a non-inverting comparator. If the input signal is given to the negative terminal, then it is said to be a inverting comparator. Here these 2 diodes are connected in reverse. It is called as a clamping diode, or you can say it is a protection diodes. Since we have to make these 2 input voltages as equal, and if you give a higher voltage to these input terminals, then it will affect the operational amplifier. So, these 2 diodes makes the voltage across these 2 terminals as either positive 0.7 volt or negative 0.7 volt, that is the cut-in voltage of the diode to protect the operational amplifier in any of the case. So, here the input voltage is given to the positive terminal and positive reference is given to the negative terminal. Here the reference voltage is taken as 1 volt, and the waveforms shows that how the comparator works under the open loop configuration. So, input signal, which is an alternating signal, so it crosses the reference voltage, which is a DC voltage at 1 volt. So, when you compare the reference and the input signal at this up to this point, so input signal is lesser and the reference signal is higher. But the reference signal is given to the negative terminal. So, the output will be a negative V saturation value. So, here until this point, until the reference voltage is higher, the voltage is negative V saturation, and the output is, the input of the comparator is higher here, higher than the reference voltage. So, input is given to the positive terminal, and if it is high, then the output will be a positive saturation voltage. So, until this point, until the reference voltage is lesser than the input voltage, the output voltage is a positive V saturation. And when you look at the other halves of the input signal, if the reference voltage is higher, then the output will have a negative V saturation. If the input voltage is higher than the reference voltage, then the output will have a positive saturation. This is for a positive V reference value. For a negative V reference value, say it is a minus 1 volt, and always the V reference is given to the negative terminal, and so the Vi is, if whenever the input voltage is higher than the reference voltage, then the output voltage will get a positive saturation. Whenever V reference is higher than the input voltage, then the output will have a negative transition. So, if this voltage is positive, if the voltage present at the positive terminal is higher, you get a positive V saturation. If voltage at the negative terminal is higher, you get negative V saturation. This is the function of a comparator, whatever may be the reference voltage. So, these input output waveforms shows for positive V reference as well as for negative V reference. And why it is a non-inverting comparator is the signal is given to the positive terminal of the operational amplifier. So, it is a non-inverting comparator. And next is inverting comparator. Here the signal is given to the inverting terminal. The alternating signal is given through the resistance to the inverting terminal of the operational amplifier, and positive terminal is given with V reference voltage. V reference, it is actually taken from the supply voltage of the operational amplifier, and these two diodes makes the voltage difference between these two terminals as always plus or minus 0.7 volts in order to protect the operational amplifier for higher values of the input voltages. And we know that according to the comparator function, the voltage at the positive terminal is higher, then it gives a positive V saturation. If the voltage at the negative terminal is higher, then the output will be a negative V saturation value. If the reference voltage is either a positive value or a negative value, this is the output. So, here consider the reference voltage as 1 volt and it is a positive value. We know that whatever voltage is higher, and according to the magnitude of the voltage given to the positive or a negative value, the corresponding saturation value will be the output. So, up to this, the reference voltage is higher and reference voltage is given to the positive terminal, so output is positive. And after this, Vi is high and Vi is given to the negative terminal, so the output is negative V saturation. Similarly, it goes on for other halves of the input signals. And if the reference voltage is negative, again the same. If the reference voltage is negative, which is given to the positive terminal, and if Vi is greater, the negative V saturation obtains at the output, and if reference voltage is greater, positive V saturation obtains at the output. Here until this, the Vi is higher, so Vi is given to the negative terminal, so it has a negative V saturation. And if V reference is higher than Vi, V reference is given to positive terminal, so it shows a positive V reference, and after that the Vi is higher, so Vi is given to negative terminal, so minus V saturation. This is the function of an inverting comparator and non-inverting comparator. So, try to answer for these questions. What is a single coherent analog multiplier? List the applications of analog multiplier. What is a comparator? Draw the output waveform for an inverting comparator with V reference 2 volts and Vi 6 volts peak to peak. In this session, we have seen analog multiplier and some of the applications of analog multiplier such as frequency doubler, voltage divider and voltage squarer. And one of the circuit in open loop configuration of operational amplifier as a comparator, in which there are two types of comparators, inverting comparator and non-inverting comparator we have seen with its input output waveforms. These are the references. Thank you.